Hello and welcome to a new video. In this video we'll talk about some of the design documents, specifically in the instrumentation and control discipline. Before we go into this, we will look at any design document cycle. What would the cycle would be, starting with a feed or FEED, front-end engineering design, or somebody will call it basic engineering or conceptual engineering, and then it moves into the design phase and detailed design, and then during the construction, commissioning, operation, and the decommissioning at the end of the life cycle of the plant itself. In the first phase, which is a design phase, you do all the designs, and then during the construction and commissioning, you don't do design. What you do is two things: either modification and at the end we call it as built. Then during the operation you may do some changes. The engineering in this middle section is very minimum. However, we go into each one of those phases. You can find many and multiple issues of the drawing itself. So it could be issued for a squad check, issued for review, for approval, for design, for a HAZOP, issued for inquiries. Then there is a final issue of each drawing, which is, let's say, issued for information, issued for construction, or issued for purchase. So those are the one which is, as we can call it, is the final stage of a design document. When you do the as-built, after that you may change the IFC to issued for information only. That's based again on each design company and the client itself. Now we'll look at the INC. We know that any document INC will produce may go by itself or may go to another discipline, so they can build their own design on our feed from INC. So on the other hand, you may also take some design documents from another discipline to produce your own design as INC. This is a typical list. Maybe I'm missing some, but this is in general, this is the most common documentation, like the database, datasheets, RFQs, RFPs, which is the requisition for purchase and for quote, index, and we will go into some of those, the most familiar one or famous one. Let's start with the database. Database is where you get all the instrumentation and your control bits and pieces together. And this database can be made by many companies. Some of them is very famous, like Intools or SPI and Bentley and all those guys. They have a very good database which can be linked to another database from other discipline, like electrical, like a process. And I have a separate video which display to you and explain to you how those different databases can interact and how to use these databases into checking and make sure that your data is absolutely correct in each one of them. Now we will look at how you get the data in. So you start with, let's say, on a PNID you have a valve or a transmitter. You start with this transmitter, give it create a tag, and then you attach to this tag a datasheet form, and then add to this tag, let's say if it's a transmitter, the range, the DCS high and low, and then alarms and all of those things. So in this case, if you can see, you enter some or most of this data manually. Now, if you have other database like the process, they have the process lines in the database for their smart PNID. You can import the same table of PNID list, of line list, and all those stuff. You can import them from other database into your database as a table to select it or to use it. Then another way of doing this also is sometimes I do the database on something easier like Excel, massage the data, and then get all this uploaded into Excel. Like in the serial interfaces, we have thousands and thousands of tags and ranges and things. So it was very easy if I make one copy, a template, and then copy, let's say, to another with another changing just the tag. So I create all those new items and upload it easily in the database to reduce the amount of hours consumed. Now, how you will assume how many hours you will consume in a database? There is one way they use it. They said per tag. So you look at what tags you have in your PNIDs. Let's say 1000 instrument, different instrument, on-off valves, control valve, transmitter, and you will say 1 hour per tag. So it's 1000 hours. That's mean one guy will be working for 6 months on this database. Another way is to look at the whole project, and you will say I need 2 guys to work on this database for 6 months, and then one guy will work 3 months full time, and then one guy will continue half time for another 3 months. So that is how you assume you know how much hour spent in the database. Now, once you have the database, you can create deliverables from this database. The first one, which is very famous, is the datasheet. If you don't have a database, you may have Excel sheet to put all those stuff on it. But if you have a database, then probably also you will send a small subroutine or some program to your vendor so they can fill it, those data sheets, and then when they send it back to you, they send it in the same format of your database. The database will automatically upload them, so you don't have to retype anything. In any data sheets, you will have some sections. Any transmitter will have a data sheet, control valve, anything as an instrument, you will have a data sheet for it. You may have 2 sheets, you may have 1 sheet. You may have 1 data sheet for each transmitter. You may have 1 sheet for maybe 5 or 10 or 20 pressure gauge, because all of the pressure gauges exactly the same. So what you will do is have a section here for all the specs, and then in the note you will have those tag numbers of the data sheets. Any data sheet will continue to be contains general section, which has a tag, PNID, and those stuff, and then the process data, which comes from the process discipline, and followed by another sections. Some of those sections will describe the body materials, the size, configuration, and sometimes you will put some data, and then you will say for the valve I will ask the vendor to advise what is the trim, so you will say vendor to advise, and so on. And then you will have some notes you need to give it to the supplier. Now, what you going to use the data sheets for? When you go for issued for requisition, so you need a quotation from a vendor, you send them the data sheet. When you place the order, you place it with the data sheet. So the vendor will know exactly what is accessory, what is valve, what's transmitter, what is the range, how to calibrate it, and so on. When you do the build as built, you may have changed some of the configuration of the transmitter, so you update your data sheets. The other one, which comes again from the database, is the instrument index. In the index, what we list is all our transmitters and valves. So any instrument that you purchase will be included in the instrument index. Everything inline, offline instrument, it is in the index. Now, when you supply it to the your client, it should be in some soft copy and hard copy. Soft copy will be mainly in Excel sheet. Here I gave you just some of the columns, which is maybe included, maybe more, maybe less. But if you can see each tag of a valve, let's say here, you will have the location drawing and the cause and effect and the requisition and the purchase order and maybe the manufacturer and the model and the serial and a lot of stuff. You can have it in your index. This is again, the format is not universal. You add and remove columns as you need. The next one is the range, alarm, and set points list. And mainly we use this document in our configuration for the DCS or the PLCs, because this is one document which will list all your transmitters and where is the setting of them. Like the set point in here, the first one I gave you a set point. So this looks like a PIC as a control loop. The second one is a trip transmitter, safety transmitter. So you have the high and the low setting. Why we have this sheet? This is one place which is very easy to combine all the alarms in one document. When you review your PID, you will find this data. You get it from the PID, but when you review your DCS configuration, it's perfect if you have one document which has all those data. So you can make sure that your DCS is configured correctly. Now, some people will say, I don't want to have a document which is live by itself. I need it within, let's say, the control narrative. Fair enough, but be careful if people will do this. Sometimes they scatter all this data in all the place in the control narrative. I recommend, if you would like to include it in one other document like the control narrative, keep them as a table at the end, in the middle, in the beginning, wherever, but keep them in one place, in one table. Don't scatter them in the document, so the people would do search if they would like to go and find what is the set point of a controller or something. Next is the I/O list and the I/O assignments. Again, this is something we started from the DCS, from the database, and we needed to configure our PLC and find out how many I/O we need. The assignment also is needed because sometimes you have a problem with how many signal for a card, or you can also change how many of a loop to be on the same card or something like that. So you may have some definitions of the splitting the loops. So you don't put, let's say you have a reactor, you have 5 transmitters for reading the pressures or the temperature. Do you put them on the same card or you split them into 2 cards? You know, this kind of stuff, you should have some kind of guideline you should follow in the I/O assignment. And again, you will have in some of the places, this is where you specify the I/O type. And in this case, let's say I/O1, that means it's 420 milliamps and it is loop powered. Maybe AI2 is a 420 milliamps transmitter powered, or the transmitter is powered by 120 or something. So you will have a typical for each signal. You will describe and explain the wiring drawing for this loop, and then in the I/O list and the I/O assignment, you just specify those types, typicals. So in the loop drawing, when you create them, it will be easy to create the loop drawing. Device interface list. So the interface list is your DCS or PLC may communicate with a different systems. So this is just a list. Will give you an idea of your DCS. Let's say in this case, will communicate with PLC1, which serving in the air compressor in this location, in this package, and I will communicate with it is a Modbus over Ethernet. So the main reason for a document like this, so your PLC or UDCS will configure how many communication card I need, and what is the form of communication, what is the protocol, and where they are distributed in your plant. So this is only a list of all your devices will interface with your, let's say, DCS or your PLCs. Now, once you have this, you have to create another deliverable, which is the Modbus. Let's say we call it Modbus here because we assume this is a Modbus. And you will explain exactly what data you receive or what data you will write, the format, and sometimes you will also for different type of communication. You specify how often you will update your data. Let's say if you have a scale, how many often you will read the scale, what you will going to do with this data, and so on. I have a specific video again. I will try to put it here, which explain exactly how you will do this in full details to get a very good interface with your devices. Cause and effect. So this is, sometimes they call it logic drawing, or another format of it is called the logic drawing. But in cause and effect, what we'll have some causes here and some action here. So the causes could be high level in a tank, low level in a tank, a high pressure, high temperature, or low temperature, and then what you want to do at this in this case. So in this video here, we will look at, let's say this is a typical one when you have let's say a water tank, and in this water tank you have low level. When the low level comes, you trip a pump and you close the valve. So you say low here in this tank, I will close my valve and trip my pump. So you put the tag of the pump, you put the tag of the valve, and so on, and then they close and trip. If there is a delay, you put a delay, you put an explanation of what you put there. So may you have a delay of 5 seconds, 10 seconds, to make sure that you have a stabilized low pressure or low temperature, or high pressure or high temperature. Now we'll move to another deliverable, is a control narrative. So in the cause and effect case, sometimes what you will do is how you will assume the time consumed in this cause and effect. Some of them is very easy, direct, and let's say you have 2-3 causes, and you will say it's 1 day 8 hours, 2 days 16 hours per cause and effect. Now when you go into the control narrative, it's a completely different issue, because control narrative could be very time consuming, could be 2 weeks, 3 weeks, or 4 weeks even for one control narrative. What the control narrative will do for you is explaining. This is the place where you can explain to the designer of the PLC configurator or the DCS configurator what do you want exactly he or she will do. Don't forget that the control narrative is one document, but you will need the guy will need the PNID, he will need the cause and effect, the logics. But if you can't find all those data in there, this is the place where you put all your explanation. For instance, if you would like, you have 2 pumps, and you would like, when you have the pressure goes low, you will start the second pump. So you have 2 pumps, one is running, the other one is standby. If the if the pressure goes low, you start the second pump, and then if the flow goes very low, you after certain amount of time you will stop the second pump which is you started. So the system will work automatically. Control narrative, the hours we will give it to it, as I said, could be 40 hours, like 1 week or 2 weeks, based on how complex is the control narrative and what is the information you include in it. Now, as we said, that we have a database, and then we have some product comes from the database. They like the instrument index. So you have a lot of work have been done in the control, the database itself. Now the massaging and dumping the data into the Excel will be very minimum. So it could be only 1 day or 2 days for each one of them. However, for wiring, normally you get it from the database. Most of those databases can actually draw the wiring for you, can give you the junction box details, the marshalling cabinet. So there is a lot of work here in preparation and in printing all those data. So sometimes we'll go with each, let's say, junction box will take a full day or 2 days. So part of it will be filling the database for it. Part of it will be issuing the drawing, reviewing the drawing, sending it to the document control, reviewing it back from the client, reissuing it. And so this all we will look at it when we do the man-hour estimate for any wiring drawing. A word of caution in the wiring: sometimes in the loop drawing, when you start to create the loop drawing in a DCS, the loop drawing sometimes it takes a lot of time in the generation. So sometimes it takes 5 minutes for each drawing, or 10 minutes, sometimes more or less, depending on the database and where is the database located. This is a typical loop drawing. As you can see, the device on the far left, and it's connected to a small junction box or a box where you can see all the cables coming from the device to a junction box. Here in this case we don't have a junction box, and then it goes all the way to the control system and shows where it's landing, how it's power supply, and up to the control card and the channel. And you don't need this in the construction of a loop. You need a cable schedule, you need a wiring diagram, junction box details, but you don't need this drawing during construction of cables. This drawing is used in the troubleshooting and commissioning and startup, and also if you have a problem with the loop later on, you will use this drawing. Normally the problem with, as we can say, with this drawing, it's automatically generated from the system, but sometimes it takes a long time to be generated. So and also the sequence of reviewing, it takes a long time. Another deliverables is the state transition. Sometimes it's very easy to express this the narrative of startup by the state transition. So if you have, let's say, a compressor, what you do, you press the start. So this is state 1, it's ready. You press the start, you start the lube oil, then after a few seconds or minutes you start the cooling, and then if everything is fine, you start the compressor. If the cooling failed, you stop. If the loop stops, and so on. So you explain exactly where you go from one state to another state. Sometimes you give the data about each state, what's happening, what's the valves are open, what's valves closed, and where you go from state to another state. So if you can see, assume this is your lube oil starts. If it failed, then you go back to this, or you go back to trip status. So you show whatever you like in this transition. How you explain a control system in this method, it's in this case we have the burner. You can combine it with a cause and effect, you combine it with the narrative. So based on the system, you may find one of those drawing is easier to explain to the guy who configures the system. And also, and most importantly, when you test the system, you will take this document and simulate trip, and you see where your system moving around on the state transition. How many hours per drawing? We start with at least 8 to 16 to maybe 1 week for one drawing, based again on how complex is the drawing, how many drawing you have in the system, and how many of them are exactly the same. Because sometimes you will find train 1, train 2, so you train 1 you will make it, and train 2 you will just copy and change the tag. Or in another cases, sometimes you have one generic, and then you say if it's train 1, the tags will be ending by 1, or the prefix is 1, the lane 2 will be 2, and so on. 3D modeling is one of the deliverables, which is now we see it with most of the projects. It's a collective work from all disciplines, starting from civil, structure, piping, electric, INC, and so on, HVAC, safety. And our INC guys will do a certain part of it, which is the offline instrument, junction boxes, modeling, cabling, and the cabinets, cable tray, and this system. And it allows you to go and walk through the plant and look at the access of your instrument, and if you can see, you can access instrument. Do you need a ladder? Do you need a scaffold to access something? So 3D modeling is very important. Now shows you how you remove and a valve, and how you get it out from a system, and so on. How many hours? Again, you can look at it because it's continuous working. So sometimes you say, I need one guy for the whole time period of the project, or 5 guys, or 1 team, or 3 teams. So it's again based on how many devices you're going to model, and how many cable trays and things. So most of the time we will go with the how many junction boxes, how many transmitter and valves in line instrument, mainly by piping guys. We don't model them. It's most of the time it's piping guys. From the 3D model is another thing comes out of it is the location drawing. Location drawing is where you can see where is all your instrument, inline, offline transmitters. And the way we do it is that we assume in the 3D model, we take a block there, or a cube or something, and from the database we can actually create those drawings. Each device, the problem with this drawing is if you have it from, let's say, plan view from the 3D model, it will have hundreds of things irrelevant to INC. So sometimes you spend sometimes to remove all those stuff just to show your INC items. This will help you to locate your instrument during construction, and normally you will give it by, this is your plant, and this is my small section in this plant, and you will give the longitude and altitude and the elevation, and sometimes you give it with millimeter to a relative point in the plant. Sometimes you give it with a GPS express numbers. There is a lot of work in each of those drawings. It could be one drawing, could be actually 2 days or 3 days for each one of those drawings. Again, it's unfortunately some of the deliverables, we have to estimate the number of deliverables during the quotation or the design, and then we will look at what's going on to happen when you create the loop drawing, the location drawing, and sometimes actually you don't know how many location drawing you're going to produce. So you will assume for each location, you will look at your location, how many modules you have, how many steel structure you have, and then you look at it and say, I will have 1 here, 2 there, 4 for each, let's say, boiler. The control system in this area, I don't have anything. So that is how you can estimate roughly how many location drawing you're going to produce. Control system deliverables. You have a lot of control system deliverables, starting with your panel details, power distribution, communication between the devices, architecture drawing, network drawing, block diagrams. Most of the time those comes from the DCS. If you have a DCS vendor. Sometimes if it's a PLC, so it's 1 or 2 cabinets, it's from the PLC vendor. The engineering company, most of the time, they don't produce the full spectrum of everything. Sometimes they produce only the architecture drawing or the block diagrams, but the control system details, sometimes they take it as is from the control system. So in this case, you have to account for your man-hour spent in reviewing those documents, because if you will receive, let's say, the panel details, you assume you have 10 panels. Each panel will have 5 drawing. That's mean 50 drawing. If you will spend 2 hours for each, now 2 by 50, that means 100 hours. So you can see those hours accumulating and start to go big and big. So you have to make sure that you accounted for all this scope in your work. Maybe the last one we will go through it is a construction work package. The construction work package is two things. One is description, which is you write up a write-up, you put it for the people who will do the construction. Now you will send them the loop drawing, you will send them the location drawing, you will send them the data sheets for the transmitters and things, and all of these things. But also sometimes you want the field contractor to buy a transmitter or to buy a pressure gauge. So the project will not buy 2 pressure gauges. It's very expensive to buy, and the EPC company to buy 2-3 big pressure gauges. So what you do in the construction work package, you will construct the field contractor to buy those 2 transmitter and or the pressure gauges or this junction box or specific cables to buy it and to install it. So this is a write-up, which is you give instruction to the site contractor what to do in specific cases, or how to do something, or the steps to do something. And also you will give them instruction if you want them to buy or to do something in a very specific way. Now we went through most of the design document for INC, and the next video we will go, and group of videos actually, we'll go through each and some of those deliverables in details, and we'll look at them and we'll see how they are developed. Thank you, and see you in the next video. Bye bye.